This is online lesson number 10 for Physics 12. It's Mr. Kreitch. Good to see you. And we're going to talk about electromagnetism, part one of it. It's a two-part series for sure. So good morning. First principle of electromagnetism is if you move electrons, so if electrons are moving at all, and that could be in the air, it could be in a vacuum tube, like the fluorescent tubes that you have on the ceiling, or it could be in wire. If you move those electrons, they'll create a magnetic field. They'll create magnetism. So if we look at this example right here, just a flat wire, a linear wire, it'll make a magnetic field just if you move those electrons. So when we have current, which is electrons moving, it'll make a magnetic field. And it works this way. Use your left hand for electrons, and with your left hand the thumb points in the directions the electrons are moving, and you end up having a magnetic field that goes around the wire. If I use this pen to represent the wire, the electrons are moving in that direction. If I used my left hand, my thumb points in the direction of the electron movement, and the magnetic field goes above the wire, and then over the top of the wire, and then behind the wire. What happens is it makes a circular pattern around the wire. So if I have the wire coming right at you with the electrons coming right at you, my thumb points in that direction, and the magnetic field goes in that direction around the wire with my fingers. So it goes for you in a clockwise direction around the wire. So electrons moving in a wire makes a circular magnetic field around the wire. And trying to draw a 3D diagram, if the wire is going in that direction and the electrons are going this way, then over top of the wire we've got the magnetic field going that way, and then it goes that way behind the wire. So over the top, behind, over the top, behind, over the top and behind, making a circular pattern. If you take the wire and loop it into a coil something like that one, then you can change the magnetic field from being a circular magnetic field around the wire to it's called an electromagnet. And the electromagnet behaves like a normal magnet. You would have a north pole up here, or it could be a south pole depending on how it's wound, whether it's clockwise or counterclockwise. And then of course if you have a north pole up here, you have a south pole down here. If that's a south pole, of course you have a north pole down here too. So it acts like a magnet. So if you do take the wire and make a coil of it, have current flowing through it, you can make an electromagnet. As long as the current flows, it's a magnet. If you turn the current off, there's no magnetism at all. These are used in the doors of our hallway. They hold the doors open because the current's on, and it'll attract another electromagnet in the wall. And then when we have a fire alarm, the current is turned off. The circuit breaker blows, and there's no current flowing through here, and the door is closed. This is best drawing I can do of a coil, and the coil would look something like this in reality. It's wound differently here to here, but it's the same sort of idea. This coil right here has 1, 2, 3 coils in the solenoid. The solenoid is just a whole bunch of coils stuck together, and they call it a solenoid. Sometimes they'll call it a coil, but the number of loops in here in the solenoid is 3. The number of loops in here, 1, 2, 3, 4, 5, that would be 5 loops in that solenoid. So the 5 loops in a formula that we're not going to talk about in Physics 12 this year, but you might encounter in university, that 5 loops means that the n number is 5. What they were showing in one of the videos is a coil, and they did a cross section of it, and the cross section looks something like this. I don't know how many ends, how many actual loops they had in that coil, but for our sake right here, we're just picking a solenoid or coil that has 4 loops. What they did in that diagram is had something that looked like this. They looked like X's. And then here they had little dots. And what the dots mean is the current's coming out at you. It's like an arrow coming towards you. And then these crosses mean the current goes into the page or away from you. So that X means into the page, away from you, and the dot means out of the page towards you. So again, the X means into the page, away from you, and the dot means out of the page towards you. So if we had a coil like this, and the dot was right here, it would mean that the current's coming out towards you. And so it would be coming out towards you here, down at the bottom, and then going into the page at the top. So the current would go in the wire in a looped way. And when the current in the wire, that's a coil, is going in that circular fashion, it'll make an electromagnet. And the electromagnet will have a north pole here and a south pole here, or depending on how the current is flowing, the south pole here and the north pole here. So the cool thing about moving electrons having a magnetic field is that their magnetic field can interact with another magnetic field. So if you had an electron moving, it could be deflected by a magnet. And they use this in cyclotrons in UBC at Triumph or in CERN in Switzerland. They use those magnetic fields to cause electrons or other charged particles to move in directions they want them to go in. Basically, an external magnet can cause an electron that's moving to change direction, to move in a direction that it wasn't normally moving in. In this example, we'll look at the force that a magnet has on an electron that's moving. In this case, we've got an electron that's moving this way and a magnetic field that's going that way. So magnetic field always goes from north to south. So if we have a magnetic field going that way and an electron moving this way, that magnetic field is perpendicular to the direction of the electron flow, and that's going to cause a force on the electron. All the force, the magnetic field, and the electron have to be mutually perpendicular, and they follow something called a left-hand rule. So I'll give you an example. If you have the electron moving in that direction and the magnetic field, which is pointing up that way, so we've got the electron going that way, magnetic field up, that will cause the electron to get pushed into the board. So it all follows the left-hand rule when every axis is at 90 degrees to each other. So what I mean is that, which is the electron direction, is perpendicular to the magnetic field, which is perpendicular to the direction that it's moving, and the magnetic field is also perpendicular to the direction that it's moving. They're all mutually perpendicular. So it follows something called the left-hand rule. Summarize, if you have a magnetic field, and it could be from a bar magnet, or it could be a north pole of a U magnet and the south pole of a U magnet, it'll make a magnetic field that way, and an electron traveling this way, then an electron going that way, magnetic field up, and the other fingers of your hand point into the board. And this relationship follows a left-hand rule. You have to use your left hand. Even if you're right-handed, you have to use your left hand. This is an example of electrons in a wire. So they have to go in one direction, and in this case they're going to the right. This time I've changed the magnetic field from north to south, so it's going down. And it follows a left-hand rule as well. If you have the electrons moving to the right and the magnetic field down, your fingers point out towards you, out from the board, and the wire would get pushed out towards you. So we just saw that a wire with current flowing in it can be moved by a magnetic field. That's how a motor works, and that's how a microphone works. Speaker or generator. They're all interconnected. So it's how a motor works, and it's how a speaker works. Here is example number 1, the northern lights. Happens all the time, every day. A solar wind particle from the sun, so it's just particles ejected from the sun, hit the earth all the time, but they get bent by the earth's magnetic field. This one solar particle has a charge of 5 microcoulombs, so 5 times 10 to the minus 6 coulombs. They're negative, they're electrons. And they travel at a speed of 3 times 10 to the 6 meters per second. Remember, the speed of light is 3 times 10 to the 8th, so it's 100th the speed of light. Hits the Earth's magnetic field at 90 degrees perpendicular, and the Earth's magnetic field is 60 microteslas, so 60 times 10 to the minus 6 teslas. What force does the particle feel? The program is loaded, but it explains everything that's in the question. What we're trying to do is find out what direction this force is on the electron. So the electron's coming from the sun, which is way out here, firing it towards the Earth in a easterly direction, if you want to call it that, to the right. And the magnetic field comes out of the north and into the south. The magnetic field comes out of the north, so down that way, around the top of the Earth and into the South Pole. So that magnetic field is actually pointing down at the top of the Earth. And you might wonder, why did I put south up here instead of north? Because that's the south magnetic pole of Earth. It's at our north geographic pole, or pretty close to it. It's about 1,000 miles off, or 1,600 kilometers off. So if we're here in Maple Ridge, we actually have a south magnetic pole up in northern Canada. I flew over it once. Solving for the force, you just put it into the equation, B times Q times V, and the B of Earth was 60 times 10 to the minus 6 Teslas. And yeah, same Tesla. In fact, they named the car after Nikola Tesla. And times the Q, the charge of the particle coming in. And obviously it's more than one electron. It's negatively charged though. I didn't put that in there because the negative sign only helps determine the direction. We know it's an electron. And then the speed was 3 times 10 to the 6th. And the final answer, 9 times 10 to the minus 4 newtons. Now the direction. Using my handy dandy left hand, I've got the electrons going that way. I've got the magnetic field up here at the north geographic pole pointing down. So the rest of my fingers point out towards you. So it's out of the board. Outward, right out at you.